Hello everyone, welcome to my talk. I will introduce our previous work, cost analysis of non-deterministic probabilistic programs. First, let's see a probabilistic program where R and R primer are two separate variables with predefined distributions as follows. Numbers 1 to 5 are program counters. 1 is the start counter, 5 is the end counter. Tick is a special command which will incur a cost at its execution. Then we may curious about whether this program will terminate, or more importantly, what's the expected accumulated cost if it terminates. Let's see some previous work. There are some approaches in program termination and cost analysis, such as recurrence relations, ranking functions, and theorem proving. However, they don't care about probabilistic programs. Ranking supermartingales have also been studied widely in program analysis. Their works focus on qualitative termination program, not the precise cost analysis, which is the focus of our work. Weakest precondition is mainly about expanded termination time. The most closely related work is angle. We make a detailed comparison in our paper. In particular, our approach can handle both positive and negative costs as well as unbounded costs, but it can handle only positive bounded costs. Another related work is strategy, which is about succinct Markov decision processes. However, such MDPs have only single while loops, bounded costs, and only linear bounds are obtained. In our work, we present a sound and efficient approach to obtain polynomial bounds on the expanded accumulated cost of non-deterministic probabilistic programs. In contrast to previous approaches that can handle only positive costs, our approach can handle both positive and negative costs, which is related to many real-world examples. This is the first approach that can handle such examples. Previous approaches requires one-step costs to be bounded constants, but our approach can handle unbounded variable dependence costs, which is also related to many real-world examples, such as the queuing network in our paper, whose costs depend on the length of a queue. We also can provide up and lower bounds for the expected accumulated costs over non-deterministic probabilistic programs. This is the first approach can provide lower bounds for expected accumulated costs program. More specifically, our approach can handle two cases of programs. Case 1, general unbounded costs means costs can be positive or negative, unbounded and bounded, or bounded or unbounded. Bounded update to variables means the difference between the valuations of program variables in the current step and that one in the next step of the program execution is bounded. Case 2, unbounded non-negative cost means the cost can be unbounded and negative. General update to variables means the difference above can be unbounded. To make our approach sound, we present the following results. First, we introduce the notion of polynomial cost martingales. A polynomial up cost martingales is a function h which maps program counters and valuations of program variables to a real number that satisfies three conditions. First, C1, the PUCS should be polynomial at each program counter. C2, the value of the PUCS at the end counter should be 0. C3, the pre-expectation is no more than the value of the PUCS at each program counter. Pre-expectation means the cost in the correct step plus the expected value of h in the next step of the program execution. A polynomial lower cost submartingale is similar to a PUCS. It should satisfy C1 and C2 above, but instead of C3, it should satisfy C3 primer. The pre-expectation is no less than the value of the PLCS at each program counter. Here is a PUCS for the simple while loop. We can find that there is a polynomial at each program counter, and the value of the PUCS is 0 at the end counter. Here is its PLCS. For case 1, we extend the optional stopping theorem and use our extended one to establish that PUCS and PLCS can provide a sound approach to obtain upper and lower bounds on the expected accumulated cost. The reason why we don't use the original one is that it requires the stepwise boundary difference condition, which will make the approach unable to handle unbounded differences. Below, we present the extended OST. We extended it so that the stepwise difference needn't be bounded by a constant, but instead by a polynomial in terms of the step counter n. And we also present a novel concentration condition, which corresponds to program termination. In particular, concentration property of termination time. You can see more details in these two papers. Then we present the soundness theorems. Given a non-deterministic probabilistic program P with a linear invariant and a PUCS, if P satisfies the concentration property and the bounded update property, then the maximal expected accumulated cost of the program until termination is no more than HL in V. The soundness of PLCS is similar to the soundness of PUCS, except that the subwall is no less than HL in V. For case 2, we use the well-known monitor convergence theorem to establish the soundness of a non-negative PUCS. It is similar to the soundness of PUCS, except that it requires a non-negative PUCS, and all the stepwise costs in P are always non-negative. Below, we describe the PUCS synthesis algorithm. The algorithm has 4 steps. For example, for this simple while loop, suppose we want to obtain a projected PUCS with an initial valuation V star. Then the algorithm will create a polynomial of degree 2 at each program counter, and set the value to be 0 at the end counter. This corresponds to condition C1 and C2. Next, the algorithm symbolically computes a template for pre-expectations. Then the algorithm processes condition C3, which equals the inequality. So, for example, at program count 3, the algorithm computes this polynomial by the obtained template in step 1 and step 2. Next, by Hardeman's theorem and linear invariant, the algorithm rewrites gxy on the left-hand side of the inequality above. Note that both sides of the equality are polynomials now. Then the equality are translated into several linear equations over the unknown coefficients aij's and ck's. These linear equations are generated at each program counter. Thus, the algorithm can translate C3 into a system S of linear equations over aij's and ck's. The non-negativity of H can be handled in the similar way. Finally, the algorithm calls an LP solver to find a solution of S that optimizes HL in V star. Note that we are optimizing for HL in V star, so the obtained PUCS is unable to provide the best polynomial upper bound for the expected accumulated cost of this program with an initial valuation V star. Moreover, this polynomial upper bound is valid for all other initial valuations that satisfy the linear invariance. Here is the upper and lower bounds with simulations of the simple while loop programs. We can find the results are very close. We now present some experimental results. First, we make a comparison with nego. The obtained upper bounds by Nego and our approach are very similar. Moreover, note that we can provide the lower bounds through PLCS, but Nego cannot play the lower bounds. Then we show that our approach can handle programs that no previous approach can handle. Note that the special fight example have no low bound because its update is unbounded. Here are several figures of our results. As shown, our approach can obtain tight bounds on the expected accumulated costs. In a word, where previous approach can obtain upper bounds, our approach can permit polynomial bounds for program with both unbounded positive and negative costs. It is sound for program with either general costs and bounded updates or general updates and non-negative costs. However, finding a sounder approach for general costs and general updates remains an interesting direction for our future work. Another interesting direction is finding non-polynomial bounds. Okay, that's all. Thanks.
Thank you. We have time for a few questions. I guess they're repairing the microphone, so just speak up.
Okay, so I should just speak up. All right.
Oh, you have?
I think it's better if the speaker could just repeat the question.
Okay, I'm Jens Rosberg. I have a question about possible generalization. Can you handle negative probabilities?
Negative, yeah.
Negative probabilities.
Negative prob.
I understand, but so I have a reason for asking. My reason is to see if this approach could apply to quantum computing. And in quantum computing, the probabilities can be negative. And so if you can handle that, your approach would apply to quantum computing right away. There was a whole workshop on the topic of your paper, but for quantum computing Saturday. But they all deal with negative probabilities.
Okay, I see. I'm not quite familiar with quantum programs, but I think that most of our results is based on order grid theories. So I think there is some possibility to extend our results to.
Okay, go ahead.
So I had a question about the simulation. This is something, right? Something, right?
Yeah.
So this is this is something, but you're trying to fit still a linear function, or when you're comparing your bounds, like the lower bounds you're computing the bounds with the linear solver versus the simulation. Just go back to this slide. Okay, you stop somewhere, like don't move like so. Just next slide, let's say. Next, like here. What is so simulation versus like the lower bound? So this is the simulation is trying to fit a linear function, or you're just sampling basically, not trying to fit the function.
We can obtain polynomial bounds.
So even with the simulation, with the samples that you get, you're trying to fit the function.
Yes. Well, actually, we can go to that function example. So we get quadratic function for the lower bound and for quadratic function for the upper bound.
I see. But that's using the simulated samples to fit those kind of functions.
No, we don't need to use those sample data. Originally like that we read a program and then we just perform a static analysis on the program, and we compare our results with the templates.
Yeah, and the samplings you're not fitting anything.
No.
there any other questions? If not, let's thank the speaker once more.